the ingenious design of the aluminum beverage can. Every year, nearly 500 billion of these cans are manufactured. That's about 15,000 per second. So many that we overlook the can's superb engineering. Let's start with why the can is shaped like it is. Why a cylinder? An engineer might like to make a spherical can. It has the smallest surface area for a given volume, and so it uses the least amount of material. And it also has no corners, and so no weak points, because the pressure in the can uniformly stresses the walls. But a sphere is not practical to manufacture, and of course, it'll roll off the table. Also, when packed as closely as possible, only 74% of the total volume is taken up by the product. The other 26% is void space, which goes unused when transporting the cans or in a store display. An engineer could solve this problem by making a cuboid-shaped can. It sits on a table, but it's uncomfortable to hold and awkward to drink from, and while easier to manufacture than a sphere, these edges are weak points and require very thick walls. But the cuboid surpasses the sphere in packing efficiency. It has almost no wasted space, although at the sacrifice of using more surface area to contain the same volume as the sphere. So, to create a can, engineers use a cylinder, which has elements of both shapes. From the top, it's like a sphere, and from the side, it's like a cuboid. A cylinder has a maximum packing factor of about 91%, not as good as the cuboid, but better than the sphere. Most important of all, the cylinder can be rapidly manufactured. The can begins as this disc called a blank, punched from an aluminum sheet about 3/10 of a millimeter thick. The first step starts with a drawing die, on which sits the blank and then a blank holder that rests on top. We'll look at a slice of the die so we can see what's happening. A cylindrical punch presses down on the die, forming the blank into a cup. This process is called drawing. This cup is about 88 millimeters in diameter, larger than the final can, so it's redrawn. That process starts with this wide cup and uses another cylindrical punch and a redrawing die. The punch presses the cup through the redrawing die and transforms it into a cup with a narrower diameter, which is a bit taller. This redrawn cup is now the final diameter of the can, 65 millimeters, but it's not yet tall enough. A punch pushes this redrawn cup through an ironing ring. The cup stays the same diameter as it becomes taller and the walls thinner. If we watch this process again up close, you see the initial thick wall and then the thinner wall after it's ironed. Ironing occurs in 3 stages, each progressively making the walls thinner and the can taller. After the cup is ironed, the dome on the bottom is formed. This requires a convex doming tool and a punch with a matching concave indentation. As the punch presses the cup downward into the doming tool, the cup bottom then deforms into a dome. That dome reduces the amount of metal needed to manufacture the can. The dome bottom uses less material than if the bottom were flat. A dome is an arch revolved around its center. The curvature of the arch distributes some of the vertical load into horizontal forces, allowing a dome to withstand greater pressure than a flat beam. On the dome, you might notice 2 large numbers. These debossed numbers are engraved on the doming tool. The first number signifies the production line in the factory, and the second number signifies the body maker number. The body maker is the machine that performs the redrawing, ironing, and doming processes. These numbers help troubleshoot production problems in the factory. In that factory, the manufacturing of a can takes place at a tremendous rate. These last 3 steps, redrawing, ironing, and doming, all happen in one continuous stroke in only 1/7 of a second. The punch moves at a maximum velocity of 11 meters per second and experiences a maximum acceleration of 45 Gs. This process runs continuously for 6 months, or around 100 million cycles before the machine needs servicing. Now, if you look closely at the top of the can body, you see that the edges are wavy and uneven. These irregularities occur during the forming. To get a nice, even edge, about 6 millimeters is trimmed off of the top. With an even top, the can can now be sealed. But before that sealing occurs, a colorful design is printed on the outside. The term of art in the industry is decoration. The inside also gets a treatment. A spray-coated epoxy lacquer separates the can's contents from its aluminum walls. This prevents the drink from acquiring a metallic taste and also keeps acids in the beverage from dissolving the aluminum. The next step forms the can's neck, the part of the can body that tapers inward. This necking requires 11 stages. The forming starts with a straight-walled can. The top is brought slightly inward, And then this is repeated further up the can wall until the final diameter is reached. The change in neck size at each stage is so subtle that you can barely tell a difference between one stage and the next. Each one of these stages works by inserting an inner die into the can body, then pushing an outer die, called the necking sleeve, around the outside. The necking sleeve retracts, the inner die retracts, and the can moves to the next stage. The necking is drawn out over many different stages to prevent wrinkling or pleating of the thin aluminum. Since the 1960s, the diameter of the can end has become smaller by 6 millimeters, from 60 millimeters to 54 millimeters today. This seems a tiny amount, but the aluminum can industry produces over 100 billion cans a year, so that 6 millimeter reduction saves at least 90 million kilograms of aluminum annually. That amount would form a solid cube of aluminum 32 meters on a side. Compare that to a 787 Dreamliner with a 60-meter wingspan. Now, after the neck has been formed, the top is flanged. That is, it flares out slightly and allows the end to be secured to the body, which brings us to the next brilliant design feature, the double seam. On older steel cans, manufacturers welded or soldered on the ends. This often contaminated the can's contents. In contrast, today's cans use a hygienic double seam, which can also be made faster. This can is cut in half so you can see the cross-section of the double seam. To create this seam, a machine uses two basic operations. The first curls the end of the can cover around the flange of the can body. The second operation presses the folds of the metal together to form an airtight seal. While the operations themselves are simple, they require high precision. Parts misaligned by a small fraction of a millimeter cause the seam to fail. In addition to the clamping of the end and can body, a sealing compound ensures that no gas escapes through the double seam. The compound is applied as a liquid, then hardens to form a gasket. The end, attached immediately after the can is filled, traps gases inside the can to create pressures of about 30 psi or 2 times atmospheric pressure. In soda, carbon dioxide produces the pressure. In non-carbonated drinks like juices, nitrogen is added. So why is a beverage can pressurized? Because the internal pressure creates a strong can despite its thin walls. Squeeze a closed, pressurized can, it barely gives. Then, squeeze an empty can. It flexes easily, the can walls are thin, only 75 microns thick, and they're flimsy. But the internal pressure of a sealed can pushes outwards equally and so keeps the wall in tension. This tension is key. The thin wall acts like a chain. In compression, it has no strength, but in tension, it's very strong. The internal pressure strengthens the cans so that they can be safely stacked. A pressurized can easily supports the weight of an average human adult. It also adds enough strength so that the can doesn't need the corrugations like in this unpressurized steel food can. While initially pressurized to about 2 atmospheres, a can may experience up to 4 atmospheres of internal pressure in its lifetime due to elevated temperatures, and so the can is designed to withstand up to 6 atmospheres or 90 psi before the dome or the end will buckle. Why is there a tab on the end of the can? It seems a silly question. How else would you open it? But originally, cans didn't have tabs. Very early steel cans were called flat tops for pretty obvious reasons. You use a special opener to puncture a hole to drink from and a hole to vent. In the 1960s, the pull tab was invented so that no opener was needed. The tab worked like this. You lift up this ring to vent the can and pull the tab to create the opening. Easy enough, but now you've got this loose tab. The cans ask you to please don't litter, but sadly these pull tabs got tossed on the ground where the sharp edges of the tabs cut the bare feet of beachgoers or they harmed wildlife. So the beverage can industry responded by inventing the modern stay-on tab. This little tab involved clever engineering. The tab starts as a second-class lever. This is like a wheelbarrow because the tip of the tab is the fulcrum and the rivet the load. The effort is being applied on the end. But here's the genius part. The moment the can vents, the tab switches to a first-class lever, which is like a seesaw, where the load is now at the tip and the fulcrum is the rivet. You can see clearly how the tab, when working as a wheelbarrow, lifts the rivet. In fact, part of the reason this clever design works is because the pressure inside the can helps to force the rivet up, which in turn depresses the outer edge of the top until it vents the can, and then the tab changes to a seesaw lever. Looking from the inside of the can, you can see how the tab first opens near the rivet. If you try to simply force the scored metal section into the can using the tab as a first-class lever with the rivet as the fulcrum throughout, you'd be fighting the pressure inside the can. The tab would be enormous and expensive. If you'd like to learn more about the entire life cycle of the aluminum can, watch this animated video by Rexam that describes can manufacturing and recycling. A typical aluminum can today contains about 70% recycled material. Also, Discovery's How It's Made has some great footage of the manufacturing machinery. Here are 2 different stepwise animations of the entire can forming process. And lastly, these are 2 detailed animations of the cup drawing and redrawing processes. The aluminum beverage can is so ubiquitous that it's easy to take for granted. But the next time you take a sip from one, consider the decades of ingenious design required to create this modern engineering marvel. I'm Bill Hammack, the Engineer Guy. Thanks to Rexam for providing us with aluminum cans in various stages of production, and thank you very much to the advanced viewers who sent detailed and useful responses for this video. We read every single comment. If you'd like to help out as an advanced viewer, check out engineerguy.com/preview. You can see upcoming projects and behind-the-scenes footage. For example, you can see early drafts of this beverage can video, and you can sign up to become an advanced viewer. Thanks again. These journals contain stunning images of the construction of the Titanic and its near-identical twin, the Olympic. I found these journals at the University of Illinois Library. The journals, written between 1909 and 1911, take me back to a time before the Titanic sunk. They give me a new perspective and let me appreciate the enormity of the scale of the engineering of the Olympic-class ships. So, let me share with you some fascinating details about the Titanic and its twins, the Olympic and Britannic. The story starts here in the Harland and Wolff shipyard in Belfast, Ireland. This large framework, called a gantry, surrounds the ships as they are built. It supports the overhead cranes and scaffolding used by workers as they construct the Olympic and the Titanic. Notice that just beyond the far end of the gantry lies the Belfast Harbor. Workers will build the Olympic here on the right, and then 9 months later, before the Olympic is finished, they will start on the left the Titanic. When completed, the Olympic stern, or rear end of the ship, will point toward the harbor. The ship's construction starts with its keel, seen here as a long, dark shape. The keel is the backbone of the ship and gives the ship rigidity. If we look at the keel from the land side, we see the keel blocks that support it. These wooden blocks, typically pine, separate the ship from the slip, the concrete floor of the gantry. Each keel block stands about 5 feet high, so this creates a space under the ship for workers to construct the ship. Workers build the ship outward from the keel. Here they construct the Olympic's double bottom. In pink, we see the framework that separates and supports the 2 bottoms of the ship. The second bottom is shown in orange. It's made of steel plates and is sometimes called the tank top because the double bottom contains 44 watertight tanks. Most of the tanks carried seawater used as ballast to balance and add weight to the ship, but some carried fresh water. In total, the double bottom carried over 5,000 tons of water, or about 1.5 million gallons. Once they finish the double bottom, workers erect the framing for the hull. From this view, we see the framing for the stern of the ship. It's what a worker would see standing on the tank top from the fore and looking toward the aft of the ship. That's where the harbor is. Looking closer, we see the rib-like structure on the start of the transverse frame of the ship. Workers rivet to this frame the hull, which will form the skin. So far, we've watched the Olympic's construction. In the gantry, that ship sits here in the background. In the foreground lies the keel of its twin, the Titanic. Its construction began 9 months after the Olympic. We see here, attached to the keel, the framework of the Titanic's double bottom. Notice this large claw-like mechanism lying on the ground, and these 3 hung from the cranes. These are hydraulic riveters, which workers used to install most of the 3 million rivets on the Titanic. Here we see the almost complete hulls of both the Olympic and Titanic. Work inside the Olympic progresses rapidly. The staterooms are being erected and plumbing is being fitted throughout the ship. To prepare for the Olympic's launch, workers paint the ship a light gray so it will stand out in black and white photographs, although they repainted the ship black soon after its launch so that it matched previous White Star liners. To ease the slide into the water, the slip was greased with 23 tons of tallow, oil, and soap. And then the order to release the ship was given, the hydraulic triggers were released, and the ship slid into the harbor, reaching a speed of 12.5 knots. Notice that the ship is launched backwards. There are many reasons for this, but among them is at the stern. The rear is wider than the bow, so it is more buoyant. In a mere 62 seconds after launch, the Olympic was afloat. The moment the ship hit the water is its official launch date, although it was mostly empty. Here it weighs only about 27,000 tons and so rides high in the water. The draft, the vertical distance between the bottom of the ship and the surface of the water, is only 18 feet. After it is completely fitted, it will weigh nearly twice that, 52,000 tons. With that additional weight, the Olympic will drop until the water reaches the border painted on the hull, a draft of about 34 feet. The Olympic cannot move by itself, and so a tugboat tows it to the fitting out quay where a gigantic crane loads the ship. Here the crane lifts aboard a cylindrical boiler. The final fitting, including attaching the propellers, is done in dry dock. And then, once everything is in place, the Olympic is ready for the sea. 7 months after this launch, the Titanic was launched. I have from this journal a few photos of that event, but keep in mind the Olympic got the big press because it was first. The Titanic only becomes of more interest in retrospect. This photograph shows the twins, the Olympic and Titanic. Although built side by side, this was the last time they were photographed together. Less than a year after the launch of these two giant ships, one suffered a collision that ripped a gaping hole in its side. That ship was, of course, the Olympic. In September of 1911, the Olympic departed the port of Southampton, England, sailing toward the Isle of Wight. The Olympic turned into the Solent Strait and passed a British warship, the HMS Hawke. The Hawke's commander was surprised by the Olympic's wide turn, but he managed to take a safe position behind and to the right of the Olympic. The Hawke then increased its speed to pass the Olympic, but the Olympic's wake sucked the Hawke inward rapidly. The Hawke tore a large hole in the Olympic, and below its waterline, the damage was even greater. The bow of the Hawke was completely smashed in. The Olympic limped back to Southampton, where the holes were temporarily patched with wood before returning to its home dock in Belfast for repairs. The Olympic's sibling also suffered a traumatic blow that caused it to tragically sink. I'm of course talking about the Britannic. The Britannic was the same size and very similar to the Olympic and Titanic. Although intended to be a passenger liner, the ship was drafted into military service in World War I as a hospital ship. While in the Mediterranean, it hit a mine or was struck by a torpedo and sank in less than an hour. Despite these accidents, the Olympic-class ships were great feats of design and workmanship. Just consider the propulsion system of the Titanic. The ship had 2 sets of reciprocating engines. These engines were fueled by coal, which was stored along the bottom of the ship. Exhaust gases from the boiler discharged through these smokestacks, which are frequently called funnels. Now, they don't look like funnels until you look at them the right way. They're upside-down funnels. This cross-section of the Olympic shows the boilers sitting atop the double bottom. Exhaust from the boilers is funneled up and out of the ship. It's well known that the aftmost funnel on these ships is a dummy. It was built primarily for aesthetic reasons. Although it did not service the boilers, it was used as a ventilation and extraction shaft for the engine and turbine rooms. The Titanic needed 4,000 tons of coal for a transatlantic trip, which took 24 hours to shovel into the bunkers. Here, in this photo of the SS Minnehaha, coal is being loaded into coal ports on the side of the hull. Loading coal into the Titanic worked much the same way. This loading left streaks of coal dust on the hull, and so nearly all ocean liners at the time were painted black to help hide these traces of coal. After the advent of oil-fueled ships, lighter colors became more popular. As the Titanic crossed the Atlantic, 650 tons of coal per day was shoveled into cylindrical boilers where it was burned to produce steam. These boilers were nearly 16 feet in diameter. This picture shows a single boiler. Notice the 2 workers beside it. The steam was piped to these reciprocating engines. The engines, when viewed from the front of the ship, look like this. The orange is the piston rod, and inside the cylindrical casing is the piston. This worker peering out of this casing gives a sense of the engine's size. Excess steam from these engines was used to drive a turbine engine. This shows the turbine under construction and without its outer casing. Note the workers at the top. This is huge. If you look closely, you can see that the turbine is made of hundreds of individual blades. A shaft transfers power from the engines to the propellers. The ones on the left and the right were powered by the reciprocating engines, and each propeller weighed 38 tons, while the central propeller was powered by the turbine engine. It was cast as a single piece of manganese bronze and weighed 22 tons. The outer propellers were used for tight navigation of harbors, while the central propeller was used only in open seas. Also, unlike the others, the central propeller could not be driven in reverse, only forward. Even with this powerful propulsion system, the Olympic-class ships were not the fastest at the time, which was intentional. The White Star Line decided to focus on comfort and luxury over speed. It's clear that the lavishly decorated rooms on the Olympic and Titanic certainly made the passage more enjoyable, but there were some hidden design choices that made these ships the pinnacle of comfort for all classes of service. The ships were steered using these helical gears. Each ship had two sets of both the spur gears and the beveled gears. These massive gears are nearly 6 feet across, made of solid steel, and each weigh thousands of pounds. Notice the herringbone pattern on the teeth. This pattern allowed a tight engagement of the teeth and resulted in reduced vibration transmitted to the rest of the ship. Altogether, the gearing on the Titanic weighed about 7.5 tons. This very large structural piece is called the boss arms. These arms held the shafts of the outer propellers in place, and because of their size and strength, they reinforce the hull, which reduces panting. Panting occurs when variations in water pressure, say the crest versus the trough of the wave, flex the hull inward and outward. Less flexing results in less vibration felt by the passengers. These boss arms, also called shaft brackets, were fitted 20 feet apart at the very aft of the ship. While the Titanic and Britannic both had tragically short careers, the Olympic triumphed. In its lifetime, it made over 500 transatlantic journeys, carrying over 400,000 passengers and sailing 1.5 million miles. It even spent 4 years as a U.S.-Canadian troop transport during World War I, earning the nickname Old Reliable. After 24 years of service, the ship was decommissioned and scrapped for parts. The Olympic-class ships were absolute marvels of engineering. I hope it's for their revolutionary design rather than their failures that they're remembered. I'm Bill Hammack, the Engineer Guy. I thank my advanced viewers for their useful feedback on a draft of this video. If you'd like to be an advanced viewer, sign up at engineerguy.com/support. Thanks for watching.